In this video, we solved exercise 1 from worksheet 2, and we solved in the interactive class already all of the points from A to F. There are only two missing. This is point D and point E. So what we have to do is to find the singularities of the function and to see if this singularity is removable, is a pole, or is an essential singularity. So let's start with the first function, f of z, which is equal to sine of pi z minus 2z over 1 minus 2z squared. So you will see we have a equation between two holomorphic functions. So the only problems where singularities can arise are where the denominator is 0. So f, let's call maybe this f1 and this here f2. So f1 is holomorphic for all z such that the denominator is different from 0, such that 1 minus 2z is different from 0, which means that z must be different from 1/2. So here z equal to 1/2 is a singularity, and it's isolated because it's the only one that we have is an isolated singularity. So let's see if it is removable. Okay, so what we have to do, we have to compute the limit as z goes to 1/2 of z minus 1/2 times the function. And here below, I just rewrite this term as z minus 1/2 squared, and then I have 2 squared here coming. Okay, so it's removable, the singularity, if and only if this limit is 0. So let's compute this limit. So we have here some simplification. And we get to z 4 times z minus 1/2. So now we see that for z going to 1/2, both the numerator and the denominator are 0, no? Because in the numerator we have sinus of pi over 2. This is 1 minus 2 times 1/2. This is also 1. So we can try to apply L'Hopital rule. And then we find that this is also the limit as z goes to 1/2 of the derivative of what we have above. So the derivative of the sinus is cosinus. And then we get also pi from what's inside. And then minus 2. And below we get 4 times 1. Okay, so now the denominator is not 0 anymore, so we are happy. And what happens to the numerator? It tends to pi times the cosinus of pi over 2 minus 2 divided by 4. So cosinus of pi over 2 is 0, so we get minus 1/2. So we found now a number which is different from 0. So since minus 1/2 is different from 0, the singularity is not removable, and it will be indeed a pole singularity. With order 1. Oh, the order is 1 because you see here we applied by z minus 1/2 the first power, and we get here in the end a non-zero result. So this means that the pole has order 1. Okay, so this finishes the first part of the exercise. So let's do now the other function, f2. So here the computation is very similar. So the function f of z equal to sine of z minus 1, z minus pi over 2 squared. So here we see that f has an isolated singularity for z equal to pi over 2, because it is when the denominator vanishes. So once again, let's see if this is a removable singularity. So what we have is that we have to compute the limit for z going to pi over 2 of z minus pi over 2 of the function. Right, so here we get a simplification. And once again, we have numerator and denominator going both to 0 when z goes to pi over 2. So we can again apply L'Hopital. And what we find above, we find the cosinus of pi over 2, sorry, cosinus of z. And below we get 1. So this limit is equal to the cosinus of pi over 2, which is 0. So now we find that this limit is 0, and this is then implies that the singularity is removable. So since the limit is 0, the singularity is removable. So this means that a function f can be extended to allomorphic function in also around pi over 2. So this means can be extended to a holomorphic function on a disk of some radius centered at pi over 2. Let's call this extension f tilde. And now, so this is not required by the exercise, but now maybe the question is, what is f tilde of pi over 2? So for this, what we have to compute is the limit as z goes to pi over 2 of f of z, or this was f2 of z. The limit at z goes to pi over 2 of sinus of z minus 1 divided by z minus pi over 2 squared. So here we can use again L'Hopital. And we get cosinus of z divided by 2 times z minus pi over 2. So this is still a limit of the type 0 over 0, so we can use the L'Hopital again. You get minus sinus of z divided by 2. And this is equal to minus 1/2. Okay, so in this case, we also see what is the value of the extension at the point pi over 2. So if we had from the beginning computed this limit, and we see that this limit is finite, then this also implies that already that the singularity is removable. And actually, I think you introduce removable singularities like this, so that you can give the value of the function at the singularity in such a way that the function becomes continuous and then also, of course, holomorphic. Okay, that's it.